Hello everyone. So this is the presentation of the course project for ML Foundations for Product Managers. The original problem is to build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery system to generate the power. So the data set is presented in the form of a CSV. So these are the inputs that we have: temperature, range, ambient pressure range, relative humidity, and exhaust vacuum. The target to predict or the output labels is the net hourly electrical energy output, also within a range. We were given a CSV with about 10,000 hourly readings from the sensors. So since we have historical data to predict, so this will be a supervised learning. And since we are predicting a numerical value, they will prefer we will use the regression model, so supervised regression model. There were three potential options to complete or to perform the modeling, train, and evaluate. The easiest could have been Excel. I wanted to take a slightly more, federated approach. So I used the Google Cloud's Vertex AI Auto ML. Um, I do not have an extensive programming background in Python, so I will attempt that after the this project is completed, after this course is completed. In terms of the output metric, since the range of the output values was very tight between 420 and 495, I decided to use the root mean square error, which is in general very useful when you want to accurately capture the outliers and is sensitive to their values, but not as significantly as MA, the mean absolute error. So a few things to note here is because of my choice of using Google AutoML, it did not allow for AutoML does not allow for choosing different types of algorithms. There is a predetermined algorithm that the AutoML itself decides to choose based on the input data and the output labels. Um, Also, it did not allow me to try different hyperparameter tuning for the same algorithm. It has some automated tuning already inbuilt as it goes through the training. So there, the model. So I think the model that it used was. I'll have an image that describes that. But so the only option that I was able to do was to use different input features on the same algorithm and the same hyperparameters as a different type of model. So I'll go through that, and then I attempted a different cost function just to see how that performs against different models optimized for RMSE. So now going to the model building. So the feature first step is typically is to identify what are the features that you want to use. I'm just going to start with all the available features. Google AutoML did allow me to determine what was the contribution of each feature or attribution of the output in terms of the input features. So I used that to develop the model 2, in which chose the top two features that are attributed to almost 85% of the output. So basically highly correlated to the output compared to the other two. That was model 2, choosing just two features. And model 3 is again using all the available features, but this time optimizing for MAE. And I will use the R square error for accuracy. Though this is not a direct comparison to model 1 and 2, but this is wanted to see if I use a different optimizing function, how will my accuracy be? In terms of data split for train, validate, and test, Google Cloud's option was 80-10-10, but and it would allow me to randomize. So I think this would do cross validation. But I wanted to increase the training split to 70-20-10. I thought because of the size of the data, I think we needed to be a little bit more for to validation. So I decided to use a 70-20. So how I did this was use in the CSV file, I used a random generator and used a threshold, basically zero point 0.7. Anything below zero point 0.7 is training. Anything above between zero point 0.7 and zero point 0.9 is going to be validate, and then anything greater than zero point 0.9 will be test. It's a fixed validation set that will compare M1, M2, and M3. Again, cost function choice will be root mean square error, since the output range is very tight. And then again, just for comparison's sake, we'll also have mean absolute error. So when I ran the first model, I realized that the Google Cloud version showed me how important is each feature to the final outcome, final output value. So the temperature was close to 60%, vacuum was 25%. So those two contribute to 85%. And in terms of that, you see the model used by AutoML, it was a boosted tree. So using a decisions tree with gradient boost, with the number of trees of 350, it starts with a complexity of 1, but eventually it goes down to tree complexity of 9 to the power of e power 9. So that I'm saying this is very highly complex. So it's you does this over 25 rounds during the training process, but this is something that cannot be configured. So comparing the model 1, 2, and 3, 1 and 2 for RMSE and 3 for mean absolute error. If you noticed, the model 1, which uses all of its features, shows 3.73 as the mean errors, very tight, and also has a much lower mean absolute error. Even model 3, which optimizes for mean absolute error, is unable to do that. So it's probably the model 1 is our best choice. Also to note, R square, you can see that's 0.953. It's the higher the R square value, the better the model is able to explain the variability in the output value. So that's a very highly interpretable model with 9.953 compared to the other two. So the third one it did do a good job in that aspect, almost comparable, but it was not so great with it. You got the evaluation metric of either RMSE or MAE. So I'm going to choose with model 1 as my final outcome. So this is so I use the test data to do a batch prediction of the M1 model. And as you can see, this is a visualization of the predicted outputs against the true values. So the predicted outcome is in the y-axis, the true values are on the x-axis. And if you think about it, if they should be an proper diagonal, because the scales are equal, so it should be exactly a diagonal line cutting through the chart, which how the chart looks like, the slope looks like. And as you can see that all the our predicted values are very tightly fitted around the trend line here, the mean line here. That's why the root mean square error is very low. It's actually 0.025. So it's a I have very good confidence in the model. And R square also is very high, close to 1.96. I'm pretty confident that the model that we have finally built is very good, comparing it with the test using the test data. Some quickly before we finish, quick lessons learned, mainly around the Google Cloud's Vertex AI. Lots of built-in functions, console-based, so you completely codeless. It's very useful, and it seems to be a good choice for most of the common ML tasks. But it does have low flexibility. You can't change the models easily via the console. You can, of course, if you have your custom code, if you want to build your code, that's definitely available. But if you're codeless, then it's very limited in flexibility. Cannot tune hyperparameters, cannot do cross validation, unless you go with the standard choice of 80-10-10 for the data ratio. Another problem that I had to struggle with for a few days was there is no easy way to evaluate the output prediction on only the test data. So it does evaluate on the entire data or primarily the validation set. But if you want to just take the test data and do the same way that I did like this, I thought it would be an easy way, but it was not. So I had to download all the CSV values of the batch predictions one by one, merge them, and manually evaluate the output. Now I've opened this as a question in Google Cloud, but maybe it's my lack of understanding of how the console works. And that's it. Hopefully, we learned a few. I learned a few good things about the regression model using. I also learned about Google Cloud's Vertex AI. Thank you.